Yes.
Can anyone? Okay. So we will start the this chapter, which is basically the magnetic field due to the currents, and we will see that how much strength of magnetic field will be. Uh, we will drive the relation for the strength of the magnetic field with different orientations or different symmetry of the wires. Okay. So first of all, we will start with the simple one. We will take any arbitrary shaped wire. Any arbitrary shaped wire means that it has random shape. It has no symmetry in it. And this wire, this is the wire which they have shown here. So this wire has an arbitrary shape. It is randomly. It is bending at the bottom, then it is bending at the top without any symmetry here. So first of all, what we will do is that in order to find out the magnetic field at a distance r from at a point P, which is located at a distance r from the wire from the upper end. So for that purpose, we will divide the whole wire into small differential elements. Into small differential elements means that we will cut this wire into small elements, and one of this element is equal to ds. All of these elements will have the same dimensions. Means if we are cutting, let's suppose if we have a long wire which is of 10 centimeter, we will cut it equally into 1 centimeter elements. Okay, differential elements. So this red color which is showing here is basically showing the just hold on a second. This red wire, this is the length, small element of this wire, okay, which has a length of ds, and it means that we will cut the whole wire into these small elements. Okay, so for time sake, what we will do is that we will find out the magnetic field at a point P, which is located at this point, and it has a located at a distance r from this element. Okay, from this ds element. Okay, so we will find out the magnetic field at point P due to this element, and then we will integrate the whole wire by using the limits, and we will find out the magnetic field at point P due to the whole length of the wire here. Okay, so for this purpose, what we will first of all we will cut this, and you can see here that the exactly that current is moving in the upward direction. So the we will use the current length element. Current length element means that we will take this IDS here, which is current into length element, which is DS. Okay. So we will, during our whole next procedure, we will always use current length element. And this current length element is a vector quantity, and it is the product of the scalar and that of the vector quantity here. So in order to find out the magnetic field, we will जस्ट बेटा एक सेकंड बोलिएगा पार्टिसिपेंट्स ज्वाइन कर रहे हैं ओके अच्छा अप टू दिस पॉइंट इफ एनीवन हैज एनी क्वेश्चन बेटा इज इट क्लियर टू एवरीवन
ये जरा दोबारा बता देंगे मुझे आपकी आवाज नहीं आ रही थी
जी सर बिल्कुल
बेटा
ऐसे ही
अगेन बेटा यू कैन टेक नाउ रिकॉर्डिंग
पॉज लग गया था सर आवाज में मतलब कैसे जैसे आपका माइक ऑफ है
कट गई थी सर आवाज
ओके ओके the thing is that we want to find out the magnetic field at point P due to this wire. So this is an arbitrary shaped wire. Okay, so for in order to find out the magnetic field, we will first divide this wire into small elements. Each element has a length ds, which is mentioned here. So this red color element is the element of a wire, differential element of the wire, which has a length of ds. Okay, the current is moving in the upward direction. So point P is located at a distance r from this element here. Okay, so we will use a term current length element in our derivations. The current length element is the product of the current and that of the length element. So it is a vector quantity. Okay, and we will use first we will find out the magnetic field at point P due to this element, and then we will integrate the we will integrate by using the limits, and then we will be able to find out the magnetic field at point P due to the whole wire. So right now we will only find out the magnetic field that is arising due to this element here and the current which is passing through it here. Okay, IDS. Okay, up to this point now it is clear to everyone.
और सर ये जो हमने डिस्टेंस लिया पॉइंट पी लिया ये कोई सा कहीं भी पॉइंट पी ले लिया कोई किसी खास एंगल पे नहीं लिया खास एंगल डिस्टेंस
no it's not like that. We have taken just an arbitrary point. Okay, you can take point P near to the wire or you can take it away from the wire. Okay, so we are just taking here randomly. Okay, second thing which you can see here that there they have mentioned point P, there is a cross which is no I don't know whether it is clear up to your figure. Basically this cross shows that if we will take the direction of the magnetic field, it is into the paper at the right end while it is out of the paper at the left end. Okay, so it is into the paper right now at point P and they have mentioned it here. Okay, okay, so this current length element, ठीक है. अब प्रॉब्लम क्या होता है कि the magnetic field which give rise which arises due to the current length element or the wire, its summation is quite difficult compared to the electric field because electric field is a scalar quantity because the charge element like dq which produces the electric field is a scalar quantity, charge element, while in the case of the current length element which is producing the magnetic field is a vector quantity because it is a product of. So someone is showing that diagram page is not okay. Someone texted me that diagram page was not showing on their screen. So it means that all of you are not getting the diagram page which I was showing earlier.
सर आपकी तरफ नेटवर्क इशू काफी तो बीच में चीजें मिसिंग हो रही हैं.
आपकी आवाज भी लैग कर जाती है और कभी कभार वो स्क्रीन भी आप आगे चले जाते हैं और वो स्क्रीन पीछे ही रहती है.
एक सेकंड बेटा मुझे एक सेकंड थोड़ा सा जगह चेंज करने दे देन आई विल लेट यू नो. सो यूनिवर्सिटी का नेट का बेटा ये समटाइम्स प्रॉब्लम आ ही जाता है. अच्छा आप बताएं, नो इज इट क्लियर बेटा?
जी
क्लियर?
जी सर
फिर लैग कर रही है.
क्लियर आ रही है और आपका नेट इशू हो सकता है.
चलो ठीक है, चलो बेटा. Otherwise I am giving you the recording so you can retake the lecture from there, and if anyone has a problem he can come to me during next week because you have physical psychomotor classes. Okay, so if you have any problem regarding any article you can come straight to me in department and you can meet me there. Okay, so the magnetic field which it will produce this wire, this element which I was showing earlier, okay, this one here. So the magnetic field this element ds or the current element IDS is producing at point P is given by this relation. Okay, and the relation is एक सेकंड बेटा ये मैं स्टक हुआ हूँ. हाँ, so this is
सर आपकी आवाज नहीं आ रही.
माइक ऑफ हो गया.
नेटवर्क इशू है
बेटा,
भाई.
आवाज का नहीं हुआ, नेटवर्क इशू आ गया बेटा. स्टिल आई डोंट नो व्हाट इज हैपनिंग हियर.
जी सर सबकी तरफ.
The recording has stopped.
मेरा लैपटॉप पे इट इज गेटिंग
सर रिकॉर्डिंग भी स्टॉप हो गई.
This meeting is being recorded.
कनेक्ट हुआ बेटा. Okay. So right now अब क्लियर है. Is it better?
Yes, थोड़ा बहुत.
चलें. ठीक है. Now up to this point, so this is the magnetic field that it will produce. The current length element will produce at point P, which is located at a distance r here. So here mu naught is basically the permeability. Okay, so what is the difference between the permittivity and permeability? Do you know? Can anyone tell me?
Permeability means to allow to pass.
Okay, so the difference is basically permittivity is for the electric field, and while the permeability is for the magnetic field, the lines of magnetic field that can pass through any material. So permittivity, again, when you have studied the dielectric constant or the dielectric materials in FSC, so you have used the term which was like epsilon naught or epsilon r. So basically those terms were telling you about the permittivity of the electric field through any materials. Okay, so if you have epsilon naught, it is the permittivity of the electric field due to air or vacuum, while if you are using any certain material, specific material like plastic or the glass, then the epsilon r will be used, and each and every material has different value because each and every material responds different toward the passage of the electric field. In the same way, it was just like when you were in child, we used to basically, what we used to do is we usually take two magnets, one at the top of the paper, other at the bottom of the paper, and we used to drag it by pulling them out. Okay, so it was like that. Have you ever done this?
Yes, sir.
Okay. So the thing is that some materials like paper, if it was very small, so what was happening there? Okay, it can drag it. But if we are using some plastic, it was difficult to drag this magnet on the top of the surface while using the the other magnet which was at the bottom of the surface. So each and every material has different permeability of the magnetic field. So the passage of the magnetic field lines through any material is basically represented by the permeability. So the value of the permeability here shown is for the air or for the vacuum air, which is equal to 4 pi into 10 power minus 7 Tesla. And if we are using any other material, then obviously the value of the permeability would be different. Okay, so this is the magnitude of the magnetic field which we are using here, which we are getting at the point P due to the current length element IDS, and this is the vector form of this magnitude, this magnetic field, which is equal to mu naught over 4 pi into IDS cross R over R square. Okay, so this law is basically known as the Voigt-Savart's law, and we can use it for any sort of the symmetry. Okay, so first of all, what we have to do in any sort of the symmetry is that we have to divide it into the small elements, and then we will find out the total magnetic field by integrating the whole elements and using the limits. Later on, we will find out the magnetic field at a distance P due to the straight wire, and we will also integrate the magnetic field at point P. Okay, so it will get more clear to you. Up to this point, any question, beta? Okay, so coming toward the next, this is the magnetic field due to the long straight wire. So the magnetic field, let's suppose if the magnetic field is located at a distance, if we have a straight wire and we want to find out the magnetic field, which is at a point P, which is located at a distance r. So then the magnetic field due to this wire would be this one, mu naught I over 2 pi r. Later on, we will drive this relation and then it will become more clear to you. Okay, so here they are giving just an example, practical example, that they have taken a straight wire and in the surrounding they have used iron fillings. Okay, So this iron fillings are placed on the cardboard. So when the current will pass by, so it will obviously create the magnetic field. So when it will create the magnetic field, what will happen that these iron fillings, these iron filings basically, they will be readjust themselves into this shape, which is in the circular, form. So why they are in the circular form? Because we do know that when the current passes by a straight wire, the direction of the magnetic field is in the circular form. We will take our thumb in the direction of the current. So while the curl of the fingers will give the direction of the magnetic field. So the curl of the finger basically shows that the magnetic field is in the circular form around a straight wire here. So these iron filings have readjusted themselves or orientated themselves according to the direction of the magnetic field, and they are in the circular form. Second thing, they have similarity with the electric field in a way that when you will move away from the source, what happens with the electric field? Like if you have a charge and you are moving away from the charge, so what will happen to the electric field lines? Will they get more congested or will they get less congested? क्या कहते हैं सिर्फ?
Question दोबारा पूछ.
Question repeat.
If you have a charge, obviously there a charge has electric field lines. Okay, so when you will move away from the charge, the electric field lines will get more congested or they will be less congested.
Less congested.
Obviously, because as you will move away from the charge, strength of the electric field will reduce. As a result, the electric field lines, which basically represent the charges or the strength of the electric field, they will get less congested and they will more apart from each other compared to the field lines that are near to the charge. In the same way, magnetic field, as you will move away from the wire, obviously the magnetic strength of the magnetic field will become less and the spacing between the magnetic field lines become large compared to those which are near to the wire. Okay, so how we can find out the direction of the magnetic field around a straight wire? So they have given us the example here. So let's suppose we will start with the current which is in the upward direction in this figure, second figure. So you can see here that we will take our thumb in the direction of the magnetic field. Okay, in the direction of the current, we will take thumb in the direction of the current. We will curl our fingers. So when we will curl our fingers, right hand fingers, so it is giving the circular form. So circular form is just like that. It is giving us the anti-clockwise direction here. So the paper is magnetic field lines is out of the paper in this case in the left side, while in the right side it is into the paper here. In the same way, in the figure A, if we are if the direction of the current is in the downward side, okay, so when we will cut the fingers, right hand fingers, so now the fingers on the left side will be showing into the paper, that the magnetic field is into the paper, while in this case the magnetic field is out of the paper. So this is how we can find out the direction of the magnetic field. So up to this point, any question, beta?
No.
Okay. अब आ जाते हैं कि we want to find out the proof. ठीक है जी, what is the proof of the? I was telling you, okay जी, later on we will find out the magnetic field, ठीक है, at a point P from a wire and strength of the magnetic field. So what would be the equation for that one? So, and again we will use the Boyd-Savart's law here. So Boyd-Savart's law, like we will divide the wire into small elements and then we will be able to find out the magnetic field at a point P due to the each element, and later on that we will integrate them. So this is what they have done here. You can see that they have used a Boyd-Savart's law, and this is the magnetic field due to the single element which is D as shown here, and this is the total magnetic field, and they have calculated the total magnetic field by integrating the magnetic field that have been arisen due to the individual element. Okay, so
सर कौन सा लॉ यूज कर रहे हैं?
बॉयड-सावर्ट्स लॉ बेटा, ये आपने लास्ट में जो पढ़ा है बॉयड-सावर्ट्स लॉ, ये वाली क्वेश्चन वी आर यूजिंग दिस बॉयड-सावर्ट्स लॉ. ठीक है, दिस इज द बॉयड-सावर्ट्स लॉ है. ठीक हो गया, ये है बॉयड-सावर्ट्स लॉ. Is it showing on your screen? I have highlighted it. This is the Boyd-Savart's law. ठीक है, so this we will use this relation. Okay, so एक second बेटा. This is the Boyd-Savart's law. ठीक है बेटा, clear?
जी.
Okay, अब आ जाते हैं कि it was quite easy for me. Okay, I will let you know. Okay, they have drive like this, and you have to drive it on your own. But I have driven it for you. ठीक है, so it will become more clear to you, and I have used certain assumptions. ठीक है, so those are given by these handwritten lectures. Okay, so एक सेकंड बेटा, एक सेकंड. Anything is appearing on your screen?
Yes, notes.
Yes, sir.
Okay, so this, so now you can see here that this figure is the same one which they have drawn there. So you can see here that this is a straight wire. Okay, and we want to find out the magnetic field at point P. So I have used a cross here. It means that magnetic field at this point is into the paper. So this point is located at a distance r from the wire. Okay, and this is the I have divided the wire into small elements. So this is the ds element. Okay, this ds element, since I am using the current length element, so IDS would be in the upward direction. So the angle which it is making, it is located at a distance r from the point P, and the angle which it is making is pi minus theta, because the angle which current length element is making with r is theta. So the angle which this one is the pi minus theta. So is this figure clear to you, beta?
सर एक बार एक्सप्लेन कर दें फिर.
Okay, this is the 0 point. ठीक है, let's suppose this is the 0 point here, origin here. I have started from this point. So this I have divided the wire into Okay beta, I am telling it again. ठीक है beta, I am telling it again. So this is the wire here. ठीक है, straight wire. We want to find out the magnetic field at a point P. So what I have told you earlier in the Boyd-Savart's law, that we will divide the wire into small elements. Into small elements means that we will divide into differential elements, which in this case is I have divided this one, this part ds. So the magnetic field at point P due to this element, okay, is dB here. Okay. So this element is located at a distance r. Okay, so at a distance r from the point P, and this point P is located at a distance capital R from the wire here. The angle which current length element IDS, okay, IDS would be in the upward direction, is making with this one is theta here. This is the theta here. So the angle which this angle would be equal to pi minus theta. Now is it clear to you? जी बेटा, is it clear to you?
Yes sir.
ठीक है. अच्छा, अब आ जाते हैं कि we will use Boyd-Savart's law. ठीक है, so this is the Boyd-Savart's law here. Mu naught I over 4 pi ds into sin theta over r square. ठीक है. For the half wire, which this is the origin, we have started from this point. So we are taking right now only the upper section. So for the upper section, this law would be like this one. If I want to find out the total magnetic field, okay, due to the upper half of the wire at point P. So upper half of the wire will be in this direction. So the magnetic field at point P due to this section of the wire, the total wire in the upper section would be integral dB 0 to infinity. And for full wire, when I will take the bottom side too, so for that purpose, the total would be like this one, 2 into dB. ठीक है, integral dB. एक चीज समझ में आ गई कि why I am taking 2 here?
Yes, sir.
No, sir.
एक वायर ले रहे हैं आप, ठीक है, दिस इज द वायर है, ठीक है, दिस इज द वायर है, लेट्स सपोज दिस वन इज द वायर है, ठीक है. सो आई एम फाइंडिंग आउट द मैग्नेटिक फील्ड एट दिस पॉइंट, ठीक है, P which is located at a distance R here, ठीक है. So the length of the total wire is not this one because I am taking the lower portion also exists here. So if I am calculating the magnetic field due to this section of the wire, ठीक है, this section of the wire, obviously, due to this section of the wire, obviously there will be a magnetic field due to the lower section of the wire too. Okay, so I am calculating the magnetic field due to the upper section, which would be equal to B into mu naught over dB. So for the total magnetic field would be equal to the combination of these two sections. So I will take 2 into integral dB. ठीक है, अब समझ में आ गई सी बेटा?
जी सर.
Okay. So total section would be equal to 2 into mu naught dB here. एक सेकंड बेटा, एक और चीज कर लेते हैं. I think you should be screen के तरफ देख. Yeah. एक सेकंड होल्ड कीजिएगा बेटा, स्क्रीन शेयर की है. I just shared the screen here. Is it appearing on your screen?
No, sir.
No, sir.
No, sir.
अब
Yes, sir.
Yes,
Sir,
sir.
notes show रहे हैं.
ठीक है. ओके, अब यहाँ पे इन द बुक, ठीक है, दिस इज द बुक हियर, ठीक है. अब इन दिस केस यू कैन सी दैट दिस फिगर, दिस वन इज द सेम वन व्हिच वी वर शोइंग हियर. क्लियर? ठीक है, सेम चीज है. वी हैव नॉट टेकन एनीथिंग एल्स. Only thing which is we are seeing here is this one here. Isn't it the same figure? Same नहीं है?
जी sir.
Yes, sir.
This is the current length element. It is making an angle theta with the distance which is from the point P. And this is the distance of the point P from the wire. Okay, so the current is moving in the upward direction, and you can see here this is the magnetic field due to the whole length of the wire, which is equal to, they have taken 2 into 0 into infinity dB. Okay, so they were previously taken the upper half. Okay, so for the lower half, what they have done, they have multiplied it by 2. Okay, clear?
Yes, sir.
ओके फाइन. अब आ जाते हैं टुवर्ड दी आवर नोट्स है, ठीक है. अभी स्टिल स्टूडेंट्स आर कमिंग टू दिस क्लास, ठीक है. अच्छा, सो व्हाट वी विल डू इज हियर वी विल पुट द वैल्यू ऑफ dB. सो दिस dB is equal to mu naught I over 4 pi into ds sin theta over r square. So we got this one here. So mu naught I over 4 pi into I, they are constant quantity. They are constant quantity because we do know that same current I is passing through the wire, ठीक है, mu naught is the permeability which is equal to 4 pi into 10 power minus 7. 4 pi itself is a constant, so the only variable quantities are here 0 to pi into sine theta r square over ds. Okay, so we have taken the constant quantities out of the integral, and we have divided 4 by the 2, and the result would be equal to mu naught I over 2 pi. Okay, so अब आ जाते हैं toward the further what we have to do के अब mu naught I over 2 pi ये आ गया हमारे पास, ठीक है. Now r is equal to s square plus r square. How we got this one? ठीक है, प्रॉब्लम ये है कि ये हम लोगों ने कैसे ले लिया. So if you will take the hypotenuse, तो hypotenuse क्या होता है बेसिकली, अंडर रूट क्या होता है,
पाइथागोरस थ्योरम लगाया था अभी तो,
पाइथागोरस थ्योरम, ठीक है, s square plus r square अंडर रूट. So this is what we have here, ठीक है, s square plus r square. Clear?
Yes sir, clear.
Okay. Also sin pi minus theta, which was the integral internal angle, ठीक है. So sin pi minus theta is equal to what? Sin theta ही होता है ना?
Yes, sir.
So this sin pi minus theta यहाँ पे put किया, it was equal to sin theta. So putting these values in the above equation, star equation, ठीक है. So what we are getting here is this one. Okay. So sin theta over s square plus r square whole square, ठीक है, because we have r square in the bottom, ठीक है. So sin theta is also equal to perpendicular over hypotenuse. So what is perpendicular here in the previous figure? The perpendicular was, this was the perpendicular here. This is the perpendicular and this is the base here. So perpendicular is r while the base is s. यही होगा. While the hypotenuse is this one. ठीक है. Okay. अब आ जाते हैं again toward our main questions. ठीक है, perpendicular hypotenuse. So perpendicular was r while hypotenuse was, we used the Pythagoras theorem. So equation would be like this one here. Okay. So अब आ जाते हैं कि we will put these values in the above equation. So by putting these values in the above equation, in this equation, ठीक है, putting the value of sin theta, so we got this value here. This is the relation which we got. Okay, next we will do is we will integrate it. So we cannot integrate it. This is the equation. After solving it, this is the equation which we will get here. So we have to integrate it. So we cannot simply integrate it. We will use certain assumptions here, and then we will get the final value. ठीक है
सर, मीटिंग फिर से स्टार्ट कर लें, खत्म हो गई.
चलिए मैं एंड करने लगा हूँ बेटा. ओके.